minus 1 will be like one of a few wave numbers. We know that B values are like a few wave numbers. So the moment this molecule jumps from 0 to 1, it's going to give me a spectrum which is an absorption that's sticking on like there, and I will make this assignment as 0 to 1 transition. I can have a 1 to 2 transition, and that's going to show up here. And what is the spacing here going to be? 2B. 2 to 3, 2 to 3. 3 to 4, 3 to 4. That's how the spectrum really stands out. So as these molecules are making these jumps from one level to another, and we know that the selection rule is there, very, very strict selection rule, and this delta J equals plus minus 1. We saw that when the molecule goes from harmonic to antiharmonic, what happens to the vibration selection group? It started off as delta V equal to 0, and delta V is plus minus 1, said, well, you can have plus minus 2, plus minus 3, and we call them the overtones and so on. So there was a relaxation in the selection rule when the molecule went from harmonic to an antiharmonic oscillator. When you went from a rigid rotor to a non-rigid rotor, selection rule delta J plus minus 1 still holds good. There is no relaxation on that rule. It's an absolutely strict selection rule that the molecules have to obey. It doesn't matter whether you're a rigid rotor or a non-rigid rotor. So delta J plus minus 1 is strict. Why is it strict? We'll have to go back to evaluating that integral, which we will not do at this point in time. But you keep in mind that the selection rule on J is extremely strict. You have to obey delta J plus minus 1, whether you are a rigid rotor or not, it doesn't matter. Harmonic oscillator plus minus 1. And harmonic, you have relaxation. You have plus minus 2, the overtone rule. So this is basically the pure rotation spectrum that I have drawn for you, and which will show up as a spectrum in the region of a few wave numbers. So if you were to plot them, this might be a few wave numbers, maybe 10 wave number spacing, 10 wave number spacing, 10 wave number spacing, and so on. We know that's 2B, 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 provided the molecule is a rigid rotor. But now, if I do this, what am I really doing? I'm jumping from B0, J0 to B equal to 1, J equal to 1. As far as the rotational transitions are concerned, the selection rule that I have now obeyed is delta J equals plus 1, because the upper state is 1, the lower state is 0, delta J equals plus 1 has been obeyed. What about the vibrational selection rule? I've gone from B0 to B1, therefore I'm still okay, because I have obeyed the delta V equals plus 1 selection rule. That's fine. But then what's the energy of this transition really? Oh, it's going to be many thousands of wave numbers, because the V equal to 0, J equal to 0, and the V equal to 1, J equal to 0, which is the vibrationally hot stuff, but no rotations. So 0 to 1, we saw, always happens around a few thousand wave numbers. So this transition is going to show up in a few thousand wave numbers. It's going to show up in the region of the spectrum which people are used to when you're recording with infrared spectrum. It's all in a few thousand wave numbers. So therefore, when that happens, I get this line out here, and you can see that I deliberately marked the scale as something like 2,000 wave numbers, just to give you an order of magnitude estimate. So while the one at the bottom is happening like in a few wave number scale, this is happening like a few thousand wave numbers. So that jump from B0, J0 to V equal to 1, J equal to 1 is a transition which I marked as 0 to 1. We are assuming we know that it is a B0 to B1 transition, and all I have done is just mark for you the J assignment of it. That's the next one. 1 going to 2. Still I am perfectly fine as far as my delta J selection rule is concerned. Delta V is the same, this plus minus 1 still. And that's going to give me another transition out. 2 to 3. 2 to 3. 3 to 4. 3 to 4. So you can see, while the bottom also has the same assignment, it is 0 to 1, 1 to 2, 2 to 3, and 3 to 4. All these 0, 1, 2, and 3 to the bottom all belong to the same vibration level. Whereas the ones at the top, one of them belongs to the lower energy state, and the other one belongs to the V equal to 1 state. But the selection rule on rotation, that it must be plus minus 1, in this case we are exploring plus 1, lets you have the sort of the same assignment, 0, 1, 0, 1, 1, 2, 1, 2, excepting that in one case, all the quantum numbers are in the same state. Whereas in the top one of them is in the lower state, the other one is from the upper state. I'm also making the assumption that the B values are the same for this set of levels, that set of levels, which therefore means that the spacings are going to be the same here as well as there. This that I have over here is a delta J equal to plus 1. But I can have a delta J equal to minus 1, which we saw, but in this case it shows up. And that's the one that I have shown you here. It's starting from 1 and ending up on 0. Delta V is still plus 1, but delta J now is going to be minus 1. And where will that line appear? On a lower frequency. That's 1, 0. 2, 1, 2, 1. 3, 2, 3, 2, 4, 3. Because I have drawn all these sticks on the same height. But you know fully well they can't be at the same height because the intensities eventually have to be different. And what is the intensity going to be determined by the population? And we know what the population is going to be. J max, KT, YT, all these things will reapply into this problem. And this is not complicating the issue at this point. But all we need to know at this point is to see how the spectrum stands out on both sides. While the pure rotation spectrum gives you only one series of lines, the vibration rotation spectrum gives you two series of lines, one going out that way and one going out this way. What's the spacing here? It's 2B. 2B, the same over here. And I assume the B values are the same in both the upper state and the lower state. Therefore, they all have to be equally spaced. What is the spacing? I made a little notch out here. What do you think that notch is really for? It's a 0-0 transition, which is not allowed, but which gives me the base. Everything is from there. The 0 to 0. B equal to 0, J 0 to B equal to 0, B equal to 1, J 0. That is where it should have occurred if the transition ever occurred. It's never going to occur, it's not going to happen. Because we know delta J equals plus minus 1 is a very strict selection rule. Of course, I must qualify, I should really say it will never happen. You will see later molecules which will show you that. But as of now, we are looking at molecules that will strictly obey delta J equals plus minus 1. So that notch is the impossible J0, J0 transition. What is going to be the spacing between this and this? This and this. That's 2B again. And this 2B. So when you look at the spectrum, what will happen? You'll see 2B, 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 2B on one side. You'll see again 2B, 2B. So but somewhere in the middle, you'll see a 4B spacing, a rather large spacing. That's a tip-off. That's a tip-off telling you that the moment you see 4B, everything that occurs on the high frequency side must be the which branch? R branch. And everything on the other side must be the P branch. So this 4B spacing, which is twice the normal spacing that you otherwise see, is actually telling you that is where the demarcation actually is occurring. You remember the last time we did pure rotation spectra, I told you that if you have all these spectra, the intensity goes up and then falls off. You can't say that your first line has to be the J0 to 1 line, because it's quite likely that that line had such a low intensity that you probably never saw it. So the first line that you're really seeing, quite likely it was maybe a 2-3 line or a 1-2 line. And by simply assuming that it was a 0 to 1 line, because it's the first one that is showing up, you're actually making an error in your J assignment. How did we take care of that problem? Isotopes. Because isotopic shift is going to be proportional, a little bit dependent on J assignment, and that's how we fix that isotope number. Here what happens in this spectrum? You really don't need an isotope really, because all you have to do is keep looking and see whether you see a large gap somewhere. And if you see a large gap somewhere, you can make your own conclusions as to where the whole thing starts off. So here you have some sort of a calibration that's built into the whole system to let you figure out what the J number is going to be. But again, it's quite likely that the first 2 lines you never saw, and the 2 lines that you're seeing are probably the 2-1 line and the 1-2 line, in which case what is going to be the gap there? Quite large. It will be the 8B. But still you'll be able to figure out. If everything is 2B and this is 8B, I'm missing 2 lines. And therefore you can still figure it out. And therefore you really don't need isotopic labeling to fix your J number. But in the spectroscopic community, we believe that nothing is final until you have given me an isotopically labeled spectra if you have to determine J number. So if you ever try to give all these arguments where you publish saying that I know that this is this because I saw 8 G spacing and so on, you'll never agree. So go back and do your isotopic labeling and tell me that the isotopic shifts really match up with what you have assigned. That's delta J equals plus 1 minus 1 part R, and that's P. And if you look at it, I have done this. This is by R branch. I'm just going to remember that kept in red. Red R branch. Okay. And the other one is P. And if you believe it's purple, that's P branch, purple, therefore it must be. So just to give you, of course, you mustn't be colorblind like me to be able to use this. So the point therefore is, you saw the delta J minus 1 in operation now. You never saw that in this spectrum. You saw it over here, and we said that's always going to be the case. So you can sort of anticipate that delta V equals plus 1. You're seeing, we can't see delta V equals minus 1 here, but we will see delta V equals minus 1 in the next complication that we will see later on in electronics department. And there you will see delta V equals minus 1 and other transitions. So the entire set of different selection loops will operate. We'll get to that issues at that point in time. Okay. So this basically is the way your spectrum will pan out, and that's how the spectrum will look. But just to give you a feel for what a real-time spectrum will look like, all I did was a little thing up here where this spacing actually overlaps with this. So what essentially you have done is you have recorded this region of the spectrum in the infrared region. The spacings are all the same, and therefore whatever you have studied in the infrared region, and if somebody else were to do the same experiment in the microwave region, you will find that what they have recorded and what you have recorded are basically a cut and paste the same thing. And that is true provided the B values are all the same, which we are assuming at this point in time. Come Wednesday, I'll tell you that that's not really the case, and we will see what the complications are at that point in time. Okay. That's the spectrum, the real-time spectrum, or HCM, which I'm hoping you will be able to record in a couple of weeks' time. If you were to record the spectrum of HCM, that's what you will see. You see the P branch and the R branch, but of course, note the scale. There is high frequency on that side and low frequency on this side. You always have to be careful how this is shown. If there is high frequency on that side, what should be that branch? Must be the R branch. Low frequency on this side, it must be the P branch. And therefore you have these lines, 2B spacings. Intensity goes up somewhere up there, intensity goes up somewhere up here, and the highest intensity we know has to be from the transition which is emanating from the most probable J. And most probable J is simply KT by 2 HCP square root minus the R. We know how to calculate that. Same thing. And you can also see over here that this gap suddenly is quite large. It has to be because it's a 4B gap as opposed to a 2B spacing that we saw at LS. And therefore, this is exactly what you would record if you record the spectrum of here. But there's another complication which is shown here. Every line seems to be doubled up. It's not just one line, it's two lines. And the two lines show up simply because any HCl that we prepare will always have HCl 35 and HCl 37. And 35 and 37 are the ratio 1:3. Therefore, there's nothing you can do to escape that. Natural HCl or natural chlorine containing compound is one chlorine atom. It will be the ratio 1:3, which is the natural isotopic abundance of chlorine. If you did bromine experiment, we recorded for HBr, we know bromine 79 and bromine 81 have a 50-50 abundance. Therefore, you have almost equal lines anyway. But then bromine is even worse because if you have 50-50, if you take Br2 for example, you have more bromines. The situation gets really hard. Just HBr spectrum will be very similar to what we saw earlier with the bromine 79 and 81 giving you a split of nearly equal intent. This is the spectrum of carbon monoxide. This is of course there in Banwell. I just pulled it out so we can discuss this. And whoever used this book, you can see, has been really accurate studying this. Now this is the carbon monoxide spectrum. And again you have the two branches, the gap in the middle, which is also called as a null gap. So that's where the J0 transition should occur, but it's not going to occur, and therefore you have this gap out there. It's called a null gap. And you have the two big humps, and these two big humps essentially are your P and R branches. That's a transition which is happening from 0 to 1, and you get that spectrum. But supposing you look at the 0 to 2 transition, V equal to 0 to V equals 2, what would that be? The overtone. But you should get the same rotational fanning out in the overtone also, and that is what the next one is. This almost the same spectrum that you're getting out here, but it is a transition between V equal to 0 to V equals 2, which is your first overtone. And we know something, the first overtone is actually a relaxation of a selection group. Therefore, it's not going to be very intense. And you must have reasonably sensitive machines to be able to pick it up. That's the reason why the intensity is so small for the 0 to 2. You can get 0 to 3 also, the third overtone and the fourth overtones. And there are molecules for which with sensitive methods people are able to see much higher overtones. You get a lot of information about the molecule, really. But this is what you will see. A similar rotational structure, but of very low intensity, simply because the vibrational transition is not going to be favored during the selection. So it's only a relaxation that you're really seeing. That's why you see this. This is the same spectrum out here at much higher resolution. If you go back and see, there are little peaks that you will see underneath. It's not just 2V, 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 there's some extra lines poking up. And what do you think those extra lines are? Which isotope? If you see any extra lines in the spectrum and you know it's not an impurity, but mind you, if you can see some of the extra lines, and they would just be an impurity. So don't be fooled by that. But if you know it's not an impurity, then very likely it's an isotope. And what's the isotope of carbon that you will always see in natural carbon? Carbon 13. In fact, that's what saves the day in NMR spectroscopy. Because you have carbon 13, you can go back and record a carbon NMR. 1% of, roughly 1% of carbon 13. And that's basically what you are seeing. Because it is 1%, the intensity is quite small. Because it is carbon 13, there is an isotopic shift. So, while the major spectrum that you are seeing is basically a carbon monoxide with carbon 12 or 16, what you are also going to be getting in the spectrum for free is carbon 13 or 16. So you don't have to go back and do an isotopic experiment separately. You get it for free. Buy one, get it free. And you can use that to essentially pin down your numbering. You can get so much of information simply by looking at this carbon 13 spectrum. Very often you will find the isotopic spectra are nice. They can also be a nuisance because they will keep meshing up with other spectra. They sort of mesh in with that, and of course also messing up the spectrum that you will see. So it's very hard if you have these things. So you must be careful to really figure out what's really going on. And I gave the example of bromine. In literature, there have been instances, there are reports of complete misassignment of the spectra, simply because it was bromine 7981 all getting mixed up and people making their own assignments, not taking into account the isotopic abundances and so on. So people really had to then prepare bromine, which was pure in 79 or pure in 81, isotopically pure, redo the experiment, and then they got their assignment right. Complete mess up. They made a meal of the whole assignment simply because the isotopic composition being 1:1, it really created a sort of a havoc in the whole spectrum. So you've got to be careful when you're handling isotopic species, and that's the reason why I think Banwell has shown this, and that's the reason why I wanted to see this. Simply because you have carbon 13 sticking in your spectrum, and you've got to be able to pick it up and say that this must be due to carbon 13. Of course, all this, as I said, after you've ensured there are no impurities. You don't want an impurity sitting in your spectrum, and then you wrongly assigning it to the carbon 13. That's even worse. Yeah. Sure.
The spacing seems to be increasing as the direction of the
You mean over here is there?
Yeah, I mean, there's structures, molecules, very wide.
Okay. There are two reasons for why this has happened. We haven't taken into account centrifugal disruption yet. The moment you do that, it will happen. And the other thing that you must always be careful about is make sure that your spectrometer has drawn the thing for you on linear, proper linear scale. If you really go back and put your cursor out there and see what the frequencies are, then you get the actual spacing. But in all these cases, you will find that the spacing will actually change as you go along, simply because centrifugal distortion has not been taken into account. And once you take centrifugal distortion into account, this will happen. I will not speak about centrifugal distortion as of now, but when we do electronic spectroscopy, we will, and at that point in time, the question that you have basically asked will become really more meaningful. It's not a, you said the question maybe not know, this is a lot of meaning. You will actually see when we do electronics, nowadays ask that we just put the part before the horse and be done with it, and then we will come back to the details. I said, electronic spectrum and electronic spectroscopy. I'm going from one electronic state to another electronic state. Then what am I doing? I'm changing the electronic configuration. But at the same time, what else am I changing? Vibrations and rotations. So in an electronic transition, I will see all these things all over again. But then in electronic transitions, the assumption we made that the B values are all the same would be terrible. You just can't make that assumption. Why? Because even here you can't make that assumption, as we will see a little later. Because in an electronic state, when I'm taking the electron and putting it into another orbital, what can happen to the bonding? Supposing I take the electron from a bonding orbital and putting it in an antibonding orbital, what should happen to the bond orbital and what should happen to the bonding? It will change. So there is no point in saying the ground state, the lower state B values and upper state B values are all the same. We would be stupid if we kept on believing in that. When that happens, you will find that these sort of things will happen. One of these structures, either the R or the P, one fellow will keep increasing its spacing and keep going. The other fellow will go on, will keep decreasing its spacing, and then the line will start to come back. And we will see then what sort of a mess the whole thing can create. What you are seeing now is a very slight manifestation of the phenomena that we will see a little later. So you spotted that, that's good. But we will see this phenomenon that he is talking about in all its glory when we start really doing electronic spectroscopy and looking at vibration, rotation, transitions in electronics.
So,
yeah.
the maximum for both of these is different. It's P3 and R2.
Okay. When I say it's R2, they are all having name and the notation is generally given with the lower j. Okay, so R2 really means that you're going from 2 to 3, and P3 will essentially mean it's going from 3 to 2. We have spotted it right. But what happens in all these cases is that the spectrometer's response, meaning for the same amount of light that falls from the detector, it's not going to have a flat response. So if I have, let us say, 100 photons hitting me at one wavelength and 100 photons hitting me at another wavelength, I don't get the same output because the detector has, as well as the instrument has, what we call as a response that will keep changing. So if you want to get these intensities really right, you have to make a correction for all of these. And that's the reason why you will find that sometimes there might be a 1J difference back and forth, simply because of the instrument response not being flat over the entire region of the spectrum. And that's in fact quite good by the time we get to electronic spectroscopy. Okay, so I think we will so let's look at some. So basically what I was trying to do was, the other day I just drew some pictures that were terrible, and I'm not so sure how much we really understood, and that's the reason why I made these little pictures to tell you how exactly the transitions take place and how you get the spectrum in the R branch and the P branch and how they sort of pan out. And you can, so the P and R branches give you almost the same sort of information. It's just that the information is doubled up. But we will see as we go along how when you start introducing newer and newer complications into the problem, which we haven't done yet, these would, the two branches really start giving me very consistent information. What we will do now is, let's write the energy equation for a given vibrational rotation level. What is that going to be? That's the vibrational part of my energy. On top of that, I have to superimpose my rotation. So I'm going to have plus this much plus or minus d into j into j plus 1 whole square. I think we have enough complications, so we will not worry about the d and we will come back to d later. We will simply look at the vibrational part and the rotational part, and this rotation we just keep it down to just a b back. Let's say this is v prime, v j prime. So I'm looking at the upper state, therefore it's going to be, I'm assuming that these constants are all the same for both states. What will happen to the other level, the ground level? All I'm doing is in the ladder of states I wrote for you. I'm just writing out the energy equation corresponding to the lower state and the energy equation corresponding to the upper state. What's going to be the frequency of the transition I'm going to see? It's going to be the difference of these two. So let me say that it is just a E Vj. When I do this calculation for the transition frequency, I must keep in mind the selection rules that apply. It can't be for any j to any j. It has to be for a j which belongs to this delta j plus minus 1 family. What will be this difference? Let's say I am going from 0 to 1. V equal to 0, V equal to 1. So this is going to be half omega E of here. How much will that be here? It's going to be 3 half omega E. So if I subtract these two, what would I get? 3 half minus a half. So I'm going to get omega E. What would I get here? This is going to be 1 by 4. So this is 0, this is 1 half square, so it will be 1 by 4. What would I get here? It's 3 halves. 4 square, so it's going to be 9 by 4. So 9 by 4 minus 1 by 4. In fact, this is the energy difference between V0, J0 to V1, J0. Right? Just that. We saw that. In fact, when we did the harmonic oscillator problem and then the harmonic oscillator problem, we said the energy level spacing to begin with is just omega E, but then it's one and harmonicity it becomes omega E minus 2 omega E C for a 0 to 1 transition. So all I'm saying is this is just a vibrational part without taking any J into consideration. But the J is still staring at me out here. I have to work this out. What happens over here? B J prime into J prime plus 1 minus J double prime into J double prime. I simply say that this is omega E bar. I'm just covering everything and I'm just going to call it as omega E bar. And this will be E J prime square plus J prime minus J double prime square